welcome to the course again. So, in the last classes we discussed the common polymerization protocol of radical polymerations and then the controlled radical polymerization, and where we saw that in the controlled radical polymerization, by using the concept of dormant species, how we can control the polymerations which is not possible in the free radical polymerations. So, continuation to that, in this class we will discuss the anionic leaving polymerization and then we will start the coordination polymerations. So, the basic concept we will cover here, the leaving polymerization protocol, which is we have started the concept in the controlled radical polymerization, and then here we will mainly focus on the anionic ring opening polymerization in this class today. Then we will go to the leaving polymerization by metal complexes, and we will briefly know the concept of the catalysis. The key words here: anionic polymerization, transition metal organometallic compounds and catalysts, and the very brief concept of the catalysis. So, we know about the free radical polymerization, we know now controlled and radical polymerization, how in a very intelligent way how we have done the strategy of using the concept of dormant species and controlling the polymerization. Now, we will discuss today the anionic polymerization, which is which are applicable for polyolefin synthesis. Cationic polymerization is also another way, but which is not very common in polyolefin polymerization. So, let us try to understand what is that. So, here the name suggests the anionic polymerization. So, in radical polymerization the active end was the radical. So, in anionic polymerization the active end will be obviously anion. So, let us see what is that with a one example. So, let us see if you take this monomer and take the anionic polymerization, and so you will get like this polymer. Now, let us say how we will do the anionic polymerizations. So, you have to take a initiator like this one. So, you know that this is RLI. Okay. So, this is the organometallic reagent, and this RLI may be butyl lithium, may be secondary butyl lithium. In some cases we can take methyl lithium like that. So, depending on the R, the reaction rate is varied, and also the applicability of the anionic polymerations highly depends on the R. For one example, this anionic polymerations is quite possible for the styrene monomer, for isoprene monomer, or for this butene polymer. So, let us see how does it proceed. So, if we take like say styrene molecules where R is equal to pH here, that is the phenyl. So, if you do this one and you take the RLI, okay, maybe butyl lithium, sec butyl lithium. So, this one will attack here because this is less sterically crowding, sterically hindered. So, this is the preferred position, and then what you will get here, you will get, and you will see here this is the leaving end. So, this is the leaving end, and this is anion is conjugated with the phenyl group. So, this is stabilized due to the pi conjugation. Okay. So, now what you are doing, you have now initiated the polymerization. Now, this leaving end can now react with another monomer sequentially, and finally, you will get like this. Like that, and still here it is anion. So, this is again the leaving end, and the polymerization does not stop if you do not kill this leaving end deliberately. So, we use the protic solvent or H plus, okay, or any protic solvent, as example water or methanol, and then what you do, you will get the neutral polymer by abstracting the H plus to the here. So, you will see that this polymerization is leaving. Why it is leaving? Because this end is active, okay. It does not stop or does not do any other termination, which is unlike as you have done for the as you have seen for the radical polymerization. So, here again very similar to the radical polymerization, the head to tail attack is more favored than the head. So, head to what is the head to tail, like this minus is attack to this one. So, this is the head to tail, not this center attacks to this one. So, if it attacks this one, then it is head to tail, but this is not does not happen. So, always the head to tail attack is favored, because it is sterically because this position is sterically hindered, this one. So, this attack on this side is sterically favored. So, anionic polymerization is always head to tail attack. Okay. So, not only the various initiator can be used depending upon your monomer and substrate. As I show, the most of the popular initiator is this one, but this is not limited to this category of, this is called alkyl lithium. Various initiator can also be possible, as example like aromatic initiator. So, if you react with sodium metal, you will get the C10H8, and this is a very good initiator for some of the polymers. Okay. So, the main point of the anionic polymerization is the leaving, deliberate quenching, which is unlike to the free radical polymerization. So, if you recall again the plot, if you plot this molecular weight and the conversion of monomer, you will get the linear relationship. Okay. Similar way, if you plot, that is the another way to prove that the polymerization is leaving. So, this is molecular weight, and this if you are monomer initiator ratio. Okay. So, how much mole you are taking the monomer and how much initiator you are taking, you will also get the linear relationship, okay, because this is leaving. So, if you take less initiator, then you will get the high molecular weight polymer. If you take the large amount of initiator, you will get the low molecular weight. So, depending on the stoichiometry, you can control the molecular weight of the resulting polymer. So, that is the beauty of the living anionic polymerization. So, you will see that you can get the high molecular weight polymer by changing the initiator ratio or by taking the initiator. So, if it is living, you can predetermine the molecular weight which we are synthesizing by changing the initiator and monomer ratio. So, this is a very good method not only to get the well defined polyolefin, but also to tune its microstructure and functionalizing further functionalizing of the polymer. And the controlling architecture, that is the biggest advantage of this kind of living polymerization. As I told that in many cases you may need to have the polymers, depends on the specific applications, the linear or highly branching like that. Many cases you need like a grafted kind of polymer. Okay. Many cases you need like this kind of polymers or further controlling the architecture depending on your applications. And if your polymerization is not living or not controlled, you cannot make this kind of polymer architecture. So, this is as you see that the control radical polymerization, anionic polymerizations are the category of the living polymerization. However, in the recent times the coordination polymerization has played a major role in polymer industries for controlling the architecture and controlling the molecular weight. It has its own advantage, which we will discuss in the due courses. So, if you recall, the Ziegler-Natta catalyst was one of the first transition metal catalyst used for polymerization of polyethylene of ethylene monomer or propylene, which was discovered by Ziegler and Natta, and for this they awarded the Nobel Prize in 1963. So, this is essentially a titanium chloride, tetrachloride is a catalyst, and this catalyst works in presence of a co-catalyst which is triethyl aluminum or other alkyl aluminum. So, and what is the beauty? You see, if you do the polymerization by let us say this one, and if you do the traditional free radical polymerization, you will get the low density polyethylene when the R is equal to hydrogen. But when you will do the Ziegler-Natta catalyst, okay, I am just writing Zn means Z just Ziegler-Natta catalyst, you will get the high density polyethylene when R is equal to H. Not only that, when you will do the free radical polymerization, when R is equal to methyl, you will get atactic polymer, and very surprising, if you do the polymerization with Ziegler-Natta catalyst, you will get the isotactic polymer when R is equal to methyl. So, you will see that how the different polymerization condition governs the polymerization mechanism, and that you are getting the same composition of polymer, but different chemical structure. So, that we try to understand why. Okay. So, it is very clear that Ziegler-Natta catalyst have a tremendous impact in the polymer industry, as you can vary the crystallinity and the properties of the polymer by changing the chemical structure and the microstructure of the polymer. So, it is very obvious that polymerization growth is very much different from the free radical polymerization. So, later it was also explored VCl4 and other co-catalyst, and they are very surprising that here the syntactic polymer were observed when R is equal to methyl. So, you will see that how the polymerization mechanism differs from metal centered to metal centered. Okay. I am sure you are feeling very excited. What is the reason? Okay. How it governs the polymerization. So, we will discuss in the due courses, and after the Ziegler-Natta catalyst, we will discuss in very depth what is the advantage and what is the disadvantage in the Ziegler-Natta catalyst, when we will come to the lecture where we will follow a very systematic approach of the involved in the mechanism. So, further in the last 2 decades or so, this kind of catalysts have been developed. This is called Metallocene, where you will see this is this metal center is sandwiched between these 2 CP groups, and here where these 2 CP groups, here it is a free, not attached, okay, and here these 2 CP groups are basically threaded by a bridging atom. This bridging atom may be silicon, may be carbon, may be nitrogen. We will discuss in the future classes in depth. And also the metal-carbene catalysts, where you will see this is there is a double bond between the metal and carbon. This is also very unique in nature, which were recently developed as a homogeneous catalysts, showing excellent activity and control over the polymerization. I am sure you have heard the Graf's catalyst, and any idea what is the metal? Ruthenium. So, what is the basic structure of the Graf's catalyst? So, this is like that. So, you have this one, and this is cyclohexyl phosphine, and this is 2-chloro. So, you will see that this ruthenium is in +2 oxidation state, and you have the metal-carbene bond. This is also a very good catalyst for alkene metathesis polymerization. So, we will discuss these in a very systematic way. So, here I have given a very brief idea about the organometallic catalysts, which are the recent trend in polymerization followed in many industrial polymer industries. So, obviously, before going to the organometallic catalysts, it will be very highly benefit to understand what is catalyst, because I will be using the catalyst in the following classes. So, it is good to understand what is catalyst. I am sure in your basic courses you have very familiar with the catalysis. The catalysis I will discuss in a very brief way just to recall your memory. So, you know that one reaction like this one, A to B, A is the substrate and B is the product. Okay. So, the rate of this reaction can be expressed by Arrhenius equation. Okay. So, A is the frequency factor, all we know, the frequency factor okay, and the small k is the rate constant. Okay. And you see here the rate constant is proportional to the A, but the rate constant is inversely proportional to the activation energy, because you see is a negative exponential. So, that means if the activation energy high, the rate will be slow and vice versa. So, if we draw a reaction coordinate very qualitatively. Okay. So, this is your reaction coordinate and this is your Gibbs free energy. Then how the reaction progress. So, I will draw in a very qualitative way to understand the role of the catalyst. So, suppose this is my substrate, okay, and this is my, let us say, product, and how the reaction goes like this one, okay, and this is my activation energy. So, this is my activation energy, and what is this? This is the transition state. So, this black is uncatalyzed. Now, what will happen if you are facilitating the reaction by using a catalyst? So, what the major role of the catalyst is basically lower down the activation energy, and how does it do? I am showing in a very qualitative way. So, here you will see that okay. So, here you will see that the green is the catalyzed. Now, what will be the your activation energy? Your activation energy will be, let us say, this one. So, you will see that E A prime is much less the E A. So, you can, this one is the catalyst and substrate transition state. Okay. This one is the catalyst, substrate is intermediate, because this is the transition state and this is the intermediate. You know that the lifetime of the transition state is very low. So, it is not possible to isolate, but for the intermediate complexes in many cases it is isolable. Okay. So, that is sometimes it is a good proof that yes, the mechanism is going through this purpose, this way. So, sometimes we do routinely, we isolate the intermediate and prove the mechanism. So, this is my the catalyst and product intermediate. So, Cp is my catalyst product intermediate complex. This is my catalyst substrate intermediate complex, and this is my the associated transition state. Okay. Now, here you will see this is the product. So, eventually you are getting the same product by a different reaction pathway, following the a pathway which is much lower in activation energy. So, here you see that this is the very simple way of looking at that how the catalyst plays a role in the reactions. Is basically you will see that if activation energy is much low, then obviously as the rate constant is inversely proportional to the E A. So, that means the rate will be much higher for this catalyzed reaction. Okay. So, there are various inorganic and organometallic catalysts which are popularly used in industry. Do you have any idea? Can you tell me any one of them which are routinely used in industries? I am sure you know. Okay. I just list out the main purpose to give a knowledge how these organometallic or transition metal complexes have plays a role in industries and to synthesize a value added compounds. As example, I am sure you know that cobalt carbonyl complex which are used in hydroformylation reaction. I will also tell the specific industry which has a patent or discovered first. So, CO2 cobalt carbonyl catalyst, and this was discovered by BASF industry, and for what? Hydroformylation reaction, or sometimes we call OXO. What is the hydroformylation reaction? So, if you take a alkane and if you simple way using the carbon monoxide and hydrogen and this catalyst, you can functionalize this alkene by hydroformylation So, here H and this side is, so you will see is a formilated at the terminal alkene. So, this is regioselective, specifically you will get the functionalization at the terminal alkene. The active catalyst, you may remember that this is H converted to okay. So, is the active species is the hydride cobalt carbonyl complex. Sorry, this is, so you see here, and again it is converted to the tricarbonyl cobalt hydride complex. This is the active species. I am sure you have read this in your previous course. So, this is very routinely used to get the formulated product in industries. So, another related catalyst used as rhodium catalyst, which has more advantage than the previously complexes. So, this is the basic structure. You will see that So, this is developed by Johnson Matthew company, and which is again used for the hydroformylation for better selectivity. And also here there is another problem, that if this step is very much important, because to get the active catalyst, but you need the carbon monoxide in this reaction. So, if there you have to maintain a critical pressure of the carbon monoxide to proceed this reaction and as well as to proceed these reactions. So, this is own disadvantage, however, it is very popular in industries. Okay. So, another organometallic catalyst popularly used is the in synthesis of acetic acid, that is the Monsanto process. So, what is the catalyst? The catalyst is RH. So, basically rhodium iodo-carbonyl complex. So, this is routinely used to make one of the key organic molecules, which is used as a precursor to make different value added or compounds. So, here you use the methanol and you use the catalyst, and you need also some iodide source HI, and you will get the. So, in all the cases you will see we are getting the organic compounds which are very important, which plays a key precursor for many organic synthesis, which these can be synthesized by very cheap materials like methanol, carbon monoxide, here see carbon monoxide, hydrogen. So, that is why it is very popular in industry. Similarly, very same to the Monsanto acetic acid process, Cativa, which is actually developed by the British Petroleum. The Cativa is nothing but just replacing the rhodium by this very similar catalyst, but just replaced the rhodium by iridium. Similarly, you know that titanium Cl4 Lr3, and also you know that which will be discussed in this course in more depth, that is the Metallocene based catalyst, which is used by or discovered by the industry Dow and Exxon. This is used for the polyethylene synthesis. So, from here it is very clear that how the organometallic catalyst or transition metal complexes are very much related to the various industrial manufacturing process. So, here in this class we have tried to understand the leaving polymerization by anionic and by metal complex catalyzed, and the some of the popular organometallic compounds used in industries. So, which definitely will motivate you in this course. So, in the next class we will discuss about the unique properties of the organometallic compounds, which will be beneficial to understand the polymerization of the Metallocene based catalysts. We will try to understand that how the metal center and the ligand governs the organometallic reactions and mechanism, which will be very helpful to understand the polymerization mechanism. Thank you.